Meet Ada, a software engineer who's come up with a great new idea for a cryptocurrency that's going to be backed by matrix computations. It's going to solve the two hardest problems in computing: cryptocurrencies and machine learning. But a key question on Ada's mind is how to implement her mining platform really efficiently. She can use CPUs, which are ubiquitous and easy to program. She can use GPUs, which use special programming models and parallelize certain kinds of kernels. She can also design her own chip and fabricate something called an ASIC, which is going to be the most efficient way to compute a specific kernel, but it's also going to take a lot of time and resources. A trade-off between these design points is using an FPGA, or a field programmable gate array, which is a funky kind of reconfigurable architecture that can be used to emulate hardware circuits, and it's widely available on public clouds like AWS. So this talk is going to be about Ada's journey, as she learns about the flexibility of FPGA's programming model, her delight in finding out about a new software programming model that allows her to write software programs that turn into hardware designs, her frustrations with some of the unpredictability of this programming model, and how language design can aid her solve some of these unpredictability challenges. Our paper specifically identified the unpredictability of the programming model I'm going to talk about and designed a language to solve those issues. So let's talk about FPGAs. There are many ways to go down from a hardware design to an FPGA. Ada can use a traditional hardware description language, or an HDL, which operates at the level of gates, wires, and clock cycles. She can also use a modern HDL, which usually come embedded in software languages like Python and Scala, and provide powerful metaprogramming capabilities. Her final choice is using high-level synthesis, a funky kind of programming model that allows her to transfer software programs written in C++ into hardware designs. To really understand the level of abstraction of high-level synthesis, or HLS, compared to HDLs, you have to realize that HDLs are fundamentally about specifying circuits. You have to work with hardware modules, and you have to connect them using wires. HLS, on the other hand, is all about computational specifications. You get to use for loops and while loops and conditionals, and they get mapped into the correct hardware structures. Now, this level of abstraction, the gap between these two programming models, is going to cause some issues. But Ada doesn't know that yet, so she happily jumps into programming her first HLS-based design. And the kernel she specifically wants to accelerate is going to be a matrix-matrix multiply. And she takes this code and she runs it through an HLS compiler, and she gets the following architecture. She has a few memories to represent the inputs and the outputs, her core computation implemented as a multiplier, which feeds an accumulator that saves the values into a local register, followed by a write back stage where the values in the local register are written back into the output memory. Ada runs this design and she gets modest speedups, 10 to 20%. But she's confused because other people have been able to get anywhere from 2x to 15,000x speedups. And she's wondering what she needs to do to get those kinds of speedups. And she realizes that she has not yet exposed the parallelism in her design. And to do this, Ada has to make something called an area latency trade-off. She has to sacrifice the resources on her FPGA and make her design bigger, but this also makes her design run faster. And these area latency trade-offs are a key part of hardware design. You don't build hardware designs just to get them to be functionally correct. You want something that computes as many values as possible while taking as few resources as possible. So Ada goes back to her design and tries to parallelize the obvious candidate here. She wants to duplicate the multipliers in the innermost loop of her design. And HLS tools recognize that this kind of parallelism is very common and provide something called a pragma, or a code annotation, specifically the pragma HLS unroll with some factor. And this denotes to the HLS compiler that we want to unroll our loop and create parallel computing elements. Next, Ada really wants to understand how unrolling factors affect the area and the runtime of her design. On the left, she maps some resource called a LUT, or a lookup table, which corresponds directly to the area of her FPGA design. And on the right, she maps the runtime, which corresponds to the latency of her design. And she builds these designs by varying the factor of unrolling and runs them on Amazon's AWS F1. She's hoping that the area will generally go up while the runtime generally goes down. But the numbers she gets are really weird. The area is mostly flatlined, and the runtime sometimes seemingly goes up when increasing the parallelism factor. So what's going on here? To understand what went wrong, we have to focus in on Ada's hypothetical architecture, specifically this part, where Ada hopes that the memory is providing one value to each multiplier and having them operate in parallel. Unfortunately for Ada, memories on FPGAs are unlike processor memories. They are very low-level circuits that have physical constraints. A specific constraint of FPGA memory is that they can only service one read or write every cycle, which means only one multiplier will ever be active in Ada's design. Unfortunately, this means that there will be designs where increasing the parallelism factor is actually going to make it slower because we have all this extra logic that decides which multiplier gets to go now. And this form of unpredictability is a key challenge in HLS. The HLS compiler tries to respect Ada's wishes by creating more processing elements, but then it has to solve for this weird physical constraint that memories have that was never exposed to Ada. Ada doesn't know about this specific constraint, so the HLS compiler is going to add more processing elements and then patch them up. Having this unpredictability makes it really challenging to explore the area latency trade-offs, which are a requirement of good hardware design. But anyways, happily for Ada, she wasn't the first person to run into this specific issue, and she figures out a way to parallelize her design while running it faster. The solution for Ada was using yet another code annotation. This one is called pragma partition with some factor, and partitioning works over memories. A partition pragma says that take my logical memory, in this case say M1, and create distinct physical memories that each have disjoint sets of elements from the original M1. Now, because these are real physical memories, in this case 3 real physical memories, they're each going to be able to service reads in parallel, which allows Ada to have the parallelism in the design that she expected. Again, she takes her unrolling factor and the partitioning factor and she varies them in lockstep. And she again maps the area of her design versus the runtime. And this time, the numbers are even more weird. The runtime does seem to go down. She sees almost a 4x speed up in her unrolled designs, but the area is very bumpy. It seems to go up and then suddenly jump down. Weirdly, there's a subset of points that seem to behave predictably. When increasing the unrolling factor, the area always goes up and the runtime always goes down. So Ada jumped into the world of HLS programming, and she used her first C++ program to design a hardware circuit, and it really worked. She was really happy. But then she keeps running into these weird issues where she's almost fighting the HLS compiler to do the right thing. And maybe you're hoping that there's some book that has all the secrets of HLS that Ada can just read and become an expert in using these tools. But I'm sorry to say that these are just symptoms of a deeper underlying problem. The real problem is that the language doesn't capture the timing and the resource constraints of the programming model. FPGA resources have physical constraints. For example, memories can never service 2 reads or writes in the same cycle if they don't have the right resources. And we have to talk about those constraints to actually make this programming model work out. And this unpredictability has a real cost. Ada had to try out 16 designs, which corresponds roughly to 32 hours of compilation, because compiling a design into an FPGA is a time and resource intensive task. If she had some magical oracle that could tell her that only those 4 designs are even worth considering, she could have cut down her time to just 8 hours. And as her designs get more complicated, these numbers are going to change by a lot. So we tried to build exactly such an oracle by implementing a language called Dalia that enables predictable accelerator design by statically rejecting unpredictable design points. Dalia is its own language that comes with a type checker, and it compiles down to HLS C++ with pragmas inserted. Let's take a look at some Dalia code. Dalia has memories that you can read and write values from. It generates the kind of hardware architecture you'd expect. But a key question Dalia asks is that if I have reads and writes into the same memory, can they run concurrently? And from what we know about hardware memories, we know that this is not going to be possible, which means Dalia will error out saying that the affine resource M1 has already been used in this context. And that's because memories in Dalia are affine. If you use them once in a specific context, you can never use them again. The reason Dalia asked this question about concurrency in the first place is because semicolon has a special meaning in Dalia programs. It represents an unordered composition, which signals to the HLS compiler that it is okay to reorder and parallelize program statements as long as they respect data flow. For Dalia, this means that it has to consume the affine resource for M1 because the read and write might occur in parallel. But this program should be representable as long as you can carefully guarantee that the read and write happen in different clock cycles. It is totally safe to write. To denote this, Dalia has a different composition operator called the ordered composition, which denotes to the compiler that the program statements are going to run sequentially. And for the type checker, it means it can renew the affine resource for M1, which allows M1 to occur in both the program statements. So this program is going to be legal in Dalia. These two composition operators together allow Dalia to reason about the temporally exclusive use of resources. For example, A and B can use the same memory resources because they're going to run in different logical time steps. But C cannot use resources from either A or B because it's running in parallel to both of them and it doesn't know when A finishes and when B starts. Dalia also has for loops which can be unrolled. In HLS land, this program will make an unpredictable trade-off. It will have more processing elements, but it will show no speed up in the final design. And Dalia will error out, complaining the same affine resource error it showed before. And that's because for Dalia, morally, the surface program is similar to this other program where we have duplicated the loop body manually and compose the program statements with a semicolon. Since we're trying to do parallel reads into a resource M1, we're going to again have the affine resource. Dalia also allows partitioning memories using the bank statement. So saying 12 bank 3 creates 3 physical banks and creates multiple affine resources for Dalia to reason with. In this case, Dalia will have 3 partitions, which means this program is going to make a predictable trade-off, and Dalia has to guarantee that the accesses that are going to happen touch disjoint partitions. To do that, Dalia has to reason that these access expressions all touch different memory partitions, and that is why this parallelization scheme is going to make a predictable trade-off. This is easy in the case of a single iterator, but Dalia also has to support multiple iterators. In this case, we have the iterator I and j, and for the iterator j, we're going to try to unroll the loop. In HLS land, the HLS compiler has to look at this expression and somehow prove that the expression 3 times I plus j when having j unrolled is only going to touch disjoint partitions every clock cycle. This analysis in general is going to be unpredictable because it has to prove properties about arbitrary program expressions. For example, if you replace that statement with fi of j, the analysis cannot prove anything interesting about it. Instead of relying on such an analysis, Dalia rejects this program simply and says it cannot parallelize a dynamic access pattern. To instead convince the type checker that this access pattern is parallelizable, we use something called memory views. A memory view takes a physical memory and creates a logical view over it, denoting a new access pattern. And this corresponds exactly to the hardware cost that is required to implement the indexing logic to enable the access pattern. And it also provides a proof to the type checker that this access pattern can be parallelized. For a specific case, we're going to invoke a shift view. A shift view allows offsetting by some banking factor. And this restriction about the banking factor allows Dalia to prove that the access is going to be cheap because it's only changing the banking factor, not messing with the other things that are used to index into logical partitions. Dalia also has a rotate view, which allows offsetting by an arbitrary offset. Now, rotate views are going to be costlier than shift views because they require arbitrary logic. And using the different views that Dalia has, the programming can understand parts of programs that are more worthy of optimization. Turning a rotate view into a shift view is a bigger win than removing a shift view altogether because shift views are pretty cheap. Dalia has many other features that we didn't get to talk about. It supports reduction pipelines as well as more complex views that support parallelizing other access patterns. We also have a formalism for a core calculus of Dalia along with the type soundness theorem that shows that when a program time checks, it never accesses the same partition in a given clock cycle. This is all well and good, but what does Ada really get beyond a set of error messages? Dalia rejects a lot of programs, but what is the property that programs accepted by Dalia have? Well, in the type systems universe, we have the adage, well, type programs cannot go wrong. And this means different things in different domains. For Dalia, we want to show that well-typed programs make predictable trade-offs. But predictability is a subjective and empirical property, so we have to show this using an experiment. To do this, we do a design space exploration experiment, where we take a kernel, in our case a block matrix multiply kernel, enumerate 32,000 design points by varying factors like unrolling, partitioning, and other factors, and run estimation on each design point. And we get an estimate of the area of the design in the form of LUTs used and the latency of the design. And we get the following space of points. Even for a simple kernel like matrix multiply, the space is very complex. Next, we calculate the Pareto optimal points with respect to multiple FPGA resources and the latency. We only plot the LUTs and the latency in this case, but we have 5 resources. Next, we take all of these design points and run the Dalia type checker on them and plot the ones that are accepted by the type checker. Specifically, Dalia only accepts 354 or 1.1% of the entire design space. But this design space would not be useful if it had no Pareto optimal points. Personally, for Dalia, it does accept the Pareto optimal points. And this is really the value add of Dalia. You can take a massive design space for your HLS program, run the type checker, which is much cheaper than compiling your design, and then focus on the subspace that Dalia accepted. We have other design space exploration studies that we talk about in our paper. To end, I would like to talk about some of the future work that remains to be done that I'm really excited about. First, we've been looking at these programs that use concrete banking and unrolling factors. An obvious next step is allow Dalia to reason about these factors abstractly and give it a notion of resource polymorphism. Another interesting challenge is thinking about program modularity in the world of HLS, where programs have timing and resource behaviors that are not necessarily always going to be compositional. Finally, Dalia takes the first step in building a high-level synthesis stack that is predictable. But there are many other languages capturing different levels of abstraction, and there's a lot of work to be done there. Thank you for coming to my talk, and I hope all of you can help me bring predictability from languages down to LUTs.